So, welcome to the second exciting lump of core inorganic chemistry, the final piece of core chemistry really in your instruction with us. Today's lecture is going to be probably about 40 to 50% revision, but it's revision of something that you did in year one. So I guess it's probably necessary that we spend some time bringing that back to the front of your mind. And we are going to take it a little bit further forward today. So this is all about, we've spent most of inorganic instruction talking about molecules and complexes and things that are molecular, and basically trying to avoid thinking too hard about extended solids, and that's something of an omission which it's my job to try and sort out in the next few lectures. So this, bear in mind that what's up here is not exactly the same as what you've got, the tailored presentations. You don't have this slide, but just to make the point, that's molecules, that's mostly what we've been talking about, and that is not what we'll be talking about today. We're talking about things that will have extended either covalent or ionic bonds making lattices, those sorts of things, even if they're a crystal. We've only got van der Waals interactions between one molecule and the next, and we're not really worried about those. So we are interested in things more like that. That is a picture of a zeolite framework, which has got silicons, aluminiums and oxygens into this pseudo-infinite array. And it's that property that makes it very, very high melting refractory materials. This one particular one's got holes in it that suck water up. If you know about the little brown bits of molecular sieves, some of you that have been doing synthetic chemistry perhaps familiar with the little brown pellets that you get. Any nods for making things dry? None of you come across molecular sieves yet? That's worrying, because this is important stuff. Not only do they suck up moisture and keep things dry, but they also catalyse chemical reactions. So we need to know about this stuff, and it's a bit of a, as I say, it's a bit of a gap in the course. We haven't spoken about it more up until now, but that's what we'll be doing with Mondays and Tuesdays for the next 4 weeks or so. So we need to get used to thinking about extended solids, periodic solids, rather than just thinking about anything in these nice and neat and tidy molecules. And the reason we need to do that is listed in words in your handouts and in pictures on here. So we've got electronic properties. So most of the things that go in a mobile phone are solid state devices, and their function depends to some extent on their structure. So we need to understand structure. You've got magnetic storage devices, you've got iPod shuffles, even ones that go with your toilet paper. You've got building materials, you've got electronic materials, you've got lasers, those are solid state devices. The catalysts that go into these petrol refineries and turn crude oil into useful chemicals are all solid state chemicals. And you've got decorative effects like rubies and garnets and diamonds, and even glazes on pottery, etc. That's all solid state chemistry, so we do need to know a little bit about that. Everybody needs to know a little bit about it. So we can cut the course that we're going to cover over the next 4 weeks into just about 6 topics. Today I hope to deal with topic 1 and 2. Having given this course before, so I'm not entirely sure exactly how long it's going to last. We might have to drop Miller indices at the end. I know that you've had Miller indices introduced, but I do want to cover them again and take it a little bit further forward. If we run out of time at the end, we'll deal with that at the beginning of the next lecture. But the next lecture is about developing some of the themes we'll introduce today about the relationship or structure with the type of bonding in a compound. What would we expect if we've got an element here and an element here? We've got a very big electronegativity difference, and we would expect a particular kind of ionic 3D-dimensional structure. If we have an element here and an element here, then there's a smaller difference, and that will have an influence on which structure we might expect. So we'll talk about that next time, which will be Monday. And then we'll go on to the effects of non-bonding electrons, that is d electrons, lone pair d electrons for transition metal compounds, lone pairs for heavy p-block. They have an influence on the structure as well. It's not just spheres packing. We'll see how chemistry affects structure too. And then we'll look at the electronic properties, where we need to use band theory and understand conduction in solids, whether that be electronic conduction or ionic conduction that's behind solid state batteries that make your mobile phones work, for example. So there's lots of applicability in this sort of chemistry. And all of that stuff depends upon an understanding of defects, the fact that there is no such thing as a perfect crystal. The little imperfections in the crystal are what makes all this stuff work, so we need to understand about that. So that's what we're going to cover in my part of the course. As I say, the first two parts hopefully today, certainly the first one part today. You might well find it beneficial to do some background reading in this subject. The main source book for this material, the sort of classic text in solid-state chemistry, is this one by West. There are several copies in both libraries, both this one and the dual library, so you should be able to get your hands on that. There's the basic one, and then the solid-state and its applications is a little bit more advanced, but it covers all the same ground as the basic stuff with a few more applications. Might like it useful to look at those. And we've got a variety of others that you can read there. Also, the core text we gave you in first year has got some quite good coverage of the fundamentals of packing in it. And the classic text is from Wells. The first edition goes back to 1945. I've got a copy of the second edition, but that's been updated. It's the fifth edition now, and if you want to understand the structures of solids, then that's as good a place to look as any. But in principle, I'd say the principal book for the course is the first two. Okay, so what do we want to know by the end of this lecture? We want to know how to describe structures in terms of unit cells, that hopefully you're now familiar with the concept of unit cells. And for molecules, then that's mainly what Dr. Pritchard's been talking about. I'm going to talk about unit cells made from packing of simpler species, atoms, ions. And so we can get away with just thinking about how to pack things in the simplest, most efficient way possible, closest packing. This is revision from first year, but we need to refresh our knowledge of that. And we can describe structures of metals, for example, like this one. That's the structure of, that's the unit cell of the structure of copper, for example. It takes this form, base center cubic. You see the cube, bottom corners there, top corners there. One in the middle, in the base, so that's a base center cubic structure. And that is the structure of copper. If I was to fill the gaps in the structure, you can see a yellow, colours don't come, yeah, you can see the yellow pretty well there. The yellow octahedron in the middle, if I put an ion in there and also an ion in all these edge places, I will get this, which hopefully you might recognise as the structure of sodium chloride, rock salt. So you can explain lots and lots of ionic structures if you have a really thorough knowledge of the face center cubic close packing of spheres and how filling different gaps in that structure gives us the different solids. That's what most of today is about. And we call that hole filling because these are holes. We put atoms in the holes and we get all the different structures. And we'll cover metals and simple inorganic compounds today and how to count up and rationalise the stoichiometry. That's a one-to-one structure because it's sodium chloride, one sodium to one chloride, but we'll count up the atoms in there and some slightly more complicated cells as well, just to become, so that we can transfer a picture of a structure to a formula of a compound, which is important to be able to do. Right, so fundamental unit of structure, as you know, is the structure of a unit cell. And when you're dealing with simple compounds and we're looking at the interaction of some atoms to other atoms, the unit cell isn't necessarily quite enough on its own. I mean, that is the unit cell that describes the structure of a hexagonal close-packed lattice, but you wouldn't know that particularly from looking at one cell. In order to get all the information out, we have to, in our mind's eye at least, generate, imagine what would happen when we put more cells next to it and build up the overall three-dimensional structure, considering multiple cells together to really perceive the structure. So if I add lots of cells to that, and I make the atoms bigger, so this is several of these. One in the middle there would be looking down this axis, and we've made these a bit bigger so that they're more effectively filling the space. So that's the top one and the bottom one looking down. Here that's top one and bottom one. But also all the 1, 2, 3, 4, 5, 6, 7, 8 surrounding it. And only when you see them all packing together do you get a feel for what the actual coordination environment is. So we have to become accustomed to imagining in our mind's eye what the rest of the cells look like and what structure does that put the atoms in. So you generally need to consider more than one cell to see that. Okay, so we can describe many, many structures in terms of simple packed array of spheres. If the world was simple and atoms behaved as if they were just incompressible spheres like ball bearings or snooker balls, then you get two ways of packing very, very effectively. They are known as cubic and hexagonal close packing, short for closest packing. There is no other way to pack spheres that is more effective than this. So I'll take that collar off for a minute. And I'll take that collar off for a minute. And I'll say that looking down there, where I've got a layer, because they're all touching the bottom, these ones, I've got a flat bit at the bottom, they're all in one layer, and I've got a flat bit at the top, which is the next layer in our closest packing. If I borrow a few atoms to here, that way, I can maybe extend the cell a little bit further along that layer so that we can see that what we have here, incidentally, there's an order in for a company in Denmark. There should be these for each one of you to play with. We've ordered with thousands of these bits. You'll get to do your own here, because there's one thing watching me do this. The way that really gets this is for you to make these. So we'll do that in one of the workshops later. They're on order. Okay, but there I've extended that particular flat lattice, and you can see, hopefully a bit more clearly, that that atom has got 1, 2, 3, 4, 5, 6 nearest neighbours. Because any sphere of any size will fit together perfectly with precisely 6 nearest neighbours in one dimension. And then I can pack another 3 on top, and I could have another 3 in below that would give it a coordination number of 12. Now, that's shown on here as that looking down on our 6 coordinate, mutually 6 coordinate in in 2 dimensions in plane. Let's say that one, for example, has got 1, 2, 3, 4, 5, 6 nearest neighbours. That's hexagonally packed, and that's the most efficient packing. For one row of spheres, one plane of spheres, that is the only efficient packing there is. But I could put the next atom there, or I could put the next atom there. I couldn't put it there and there, because once I put it there, there's no room. But I've got two choices: either put it there in the blue spots, or there on the red spots. So if we call the first layer layer A, and the second layer layer B, the pale blue spheres there represent one 2-dimensional close-packed array of spheres. In 3 dimensions, the next layer could sit on either the blue ones or the red ones. So we can do that in the animation here. If we pack them on top of the red ones, then we get this. So there, where there was a red dot, there should now be a red sphere. And we've then got the blue dots that we can see that we didn't do anything with. So we've just packed in a red dot. That one there matches that dot there. That maps to that. And that's AB stacking. And so far there really isn't any other way. I could have used the blue dots, then they would just have been the same. It could have turned upside down and it would be identical. But that's really only one way. The way that it comes different is when you put the next one on. Because, alright, this is just making the point. If we put the blue dots on, then you've got AC. But AB and AC are the same. You just turn one upside down and it'll look like the other. It's only when you put 3 together that you can actually get differences. So, cubic and hexagonal are what we call the 2 different types. There's our first layer and our second layer again. A, then B. If we put the third layer on top of where the first layer was, just take them back again. There's the first one, second one, and now we're going to put the third one right on top of the first one, like that. See? So that's layer A, layer B, then layer A, then layer B. That's AB, AB packing. So I think the alert amongst you will realise that you've got some gaps in these handouts to keep you awake. Give you some work to do. So you've got a little blank in your handout like that. If it's hexagonal close packing, then it's A, B, A, B, etc. So that's hexagonal. And then these sorts of you can see that there. I put that there. You can still see that. I'm going to put that back here. What I will say is I'll point out that I can point out that atom in the that's it. Right, so can I now point out that atom? Not really. Hiding in the shadows there is an atom. And if I was to put the next atom right on top of that one, I put it there. And if I was to do that, I would have a hexagonal close packed lattice of spheres, and that would describe the structure of some of these metals in the middle. It would be A, and then B, and then A right on top of the first A. A, B, A, B, A, B is hexagonal. However, all I need to do to swap that to cubic is that. Move it. Notice there's nothing there. There's nothing in the bottom layer. I can touch right through to the bottom. There's nothing in the second layer. That's a different position, so we call that layer C. The difference between hexagonal and cubic close packing is just that. If you put the third one there, it's A, B, A, B, A, B, and it's hexagonal. If you put it there, on the third site, not above either of the first two, it's cubic. Now it doesn't look very cubic like that, but I'll show you that it is. That incidentally is a 111 Miller index plane. We'll deal with that in a second. But I'll put the last corner on, and hopefully we now see that that is a cube. We're very happy that that is a base centre cube. So if we've got A, B, A, B, it's hexagonal packing. If we've got A, then B, and then notice here, there's still little holes. They're not above A, they're not above B. Putting our next atoms there would make this hexagonal, sorry, would make it cubic. If I put them there on top of the original, it would be hexagonal. So instead of there, I'm putting them there. And that is ABC, ABC, etc. And that ABC, ABC stacking, which you'll also need to fill into your handout. ABC, ABC is called cubic close packing. I'll also put it at this point that this is also known as FCC. CCP, cubic close packing, is the same as FCC because that is a cubically close packed structure and it has base centering. FCC is just another word for CCP. You'll see both mentioned quite frequently in the literature, etc. You need to know both. So FCC equals CCP. Base centre cubic equals cubic close packed. Right, that's enough about the closest possible packing, and that is the only two ways there is. If the atoms are all the same size, those are the two most efficient ways to pack them. You can use some fairly simple geometry. I'm not going to go through it just now, but it's quite easy with geometry to show that the percentage of packing
68.
is
68.
about 74%.
Okay.
It is slightly less easy to show, but it's a fact that you can accept, that the coordination number of each atom here is 12. It's got 3 below, 6 in its own layer, and then 3 above in the next layer. So it's got a 12 coordination in the bulk solid, that's the maximum mutual coordination number you can get. Just geometry doesn't work to do anything else. So that's what you get in close packed metals. And so there's hexagonal close packing. For example, there's hexagonal close packing shown with the cells. This is how you will get beryllium and magnesium to pack. And we're exactly the same in every way, just beryllium smaller, so it's got a smaller cell edge than magnesium. The depth unit is slightly different, so that's the case with hexagonal. It's slightly different in the depth, whereas cubic, they're all the same. So that's HCP. There are some examples. There's the A layer, there's the B layer. The other one, cubic close packing, CCP. This is basically looking. This is a two-dimensional image to show looking straight down like that. So, pretty much we're looking down straight on top like that. Yes. So we've got layer A, layer B, layer C, layer A again. So that's what we've got there, filling that in. Layer A, layer B, layer C, then we can't see layer A at the bottom. That's what copper and silver do. What we're doing there is we are stacking it, looking down perpendicular to 111. 111, as I'll cover either at the end of today or the beginning of next time, is what happens when you take the corner off. So I can stick it on that flat edge, like that. So it's the layers stack on 111. That's what that means. That is a Miller index that we've seen previously with Dr. Pritchard. Right. Now, there is another form that metals take, and it is BCC, body centre cubic. And again, you should be familiar with that sort of a packing from Dr. Pritchard's course. You can get base centred, you can get body centred. So some metals do that as well, but that is, technically speaking, that is not the closest packing. It's pretty close, but it's not the most effective way of packing atoms. So the fact that these metals adopt that structure tells you a little bit about the electronic structure must be having some sort of effect that stops it. And very often you will get phase transitions. So iron has got a body centre cubic packing. I think at high temperatures it's body centre cubic, and at low temperatures it adopts hexagonal close packing. So you do get different metals adopting different structures, and that can affect how, etc. But often transition metals in the middle are body centre cubic, but they're not quite close packed. Any of you been to Brussels? Yeah, been there? I've been up there. You can actually take a lift up and go right into the middle one. I think you can get the top one. We've got a little mini design museum here. It's, you can see it from all around Brussels. It's very, very large. The biggest molecular model for body centre cubic lattice that I've ever seen. So it's a bit of a tourist attraction in Brussels. So yeah, if you want to get in about the body centre cubic structure, that's the place to go. So, as I was saying, body centre is quite closely packed, but it's not the closest possible packing. You can calculate the packing efficiency. CCP or HCP are exactly the same. Mutual coordination number of 12, packing efficiency 74%. Here it's actually quite easy to see what the mutual coordination number is. That one in the middle is contacting its 8 corners of the cube, so that's got a mutual coordination number of 8. So it's less coordinated, it's less packing efficient, 68% versus 74%. There's not a lot in it, really. But it's not, technically speaking, it's not closest packing. It's a quite close packing of spheres. And there is how these three structures are distributed amongst the periodic table metallic elements. You can see CCP is the round circles, cubic close packed, quite a few this end, a few there. HCP, hexagonal, quite a lot of the early transition metals, the ones that aren't BCC, body centre cubic, and they're alkalized mainly. Very difficult to rationalise that in much detail. It's true that certain metals will have a number of different state phases, stable at different temperatures. So I don't really expect you to learn these off in particular. It's just really only those three different fundamental, fairly simple primitive structures. Oh, I shouldn't use that word. They're not primitive, really. They describe the structures of almost all the metals. There are some that do something slightly different, whether it be one axis is elongated, and this is where the electronic factors come to influence matters. If you want to use your time while you're waiting for your bus and you've got an internet-enabled phone, there is a pretty instructive YouTube. If you go to YouTube and search Lattice Structures Part 1, you'll get animations of all this stuff again. So that'll take about 10 minutes of your time. And we'll very effectively review the first half of the lecture. Okay, so why do we need to know so much about cubically close packed structures of metals? Firstly, it's important to know about metals. Secondly, simple inorganic structures like sodium chloride, zinc sulfide, alloys, etc., 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 are rationalizable as derived from cubically close packed structures. So there is our face-centered cubic structure. We'll be emphasising face-centered cubic because it's the easiest to see, really. But there's face-centered cubic, one in each corner, one in each face. Sodium chloride, green one in each corner, green one in the face. So it's a face-centered cubic array of chlorides with metals in the gaps. There's a gap there filled by the metal. Yeah, and there's a one in the middle filling the gap in the middle. If I fill these bits, if I put that corner back on, I've made a tetrahedral hole. If I put an atom in those tetrahedral holes, I've got this one. Oops, I need to zoom out a bit. Quite all fit on. Okay, that again, one at the corners, one in the face-centered cubic in metals, but in this case, fluorines in the little holes, tetrahedral holes. So that is the structure of fluoride. Sodium chloride, rock salt, calcium fluoride, fluorite, and almost all inorganic, relatively simple ionic solid compounds can be explained in terms of filling gaps in a lattice, often a face-centered cubic lattice, sometimes a hexagonal lattice. So those sorts of structures are known as eutactic, not eutectic, that's a thermodynamical term. Eutactic structures. If it really is genuinely closest packing, then you're really talking about metals. For these eutactic structures, we often say, for example, that, coming back to sodium chloride, we often say that we can think of it as a close packed array of chlorides, where the chlorides touch and the metals sit in the holes made by the close packed lattice of chlorides. But of course the metals nestling in there will budge in and stop the chlorides from being truly closest packed. But we can think of it as a face-centered cubic lattice which is like closest packing. So usually the compounds, the cations are a little bit big for the interstitial site. Interstitial site, fancy word for hole. That is a tetrahedral interstices, or a tetrahedral hole. That is an octahedral interstices, or an octahedral hole. Right, so so we can rationalize things as filling holes in octahedral or tetrahedral sites, and they're called eutactic structures. You've got some gaps to fill in there, I think, haven't you? So for sodium chloride, we'll work out where these numbers come from in a second, I think. The problem with this material is I've worked out that inevitably we have to have a linear delivery because we're dependent upon time. But the material is all, by its very nature, is like a network. Everything is connected, but we have to deliver it linearly. So there'll be a little bit of repetition, a little bit of cyclic nature to the remainder of the lecture because everything's all connected. So that's kind of inevitable. So we'll just get the information down first of all, that if we fill all of the tetrahedral holes, all of the octahedral holes, we fill all the octahedral holes in the chloride lattice with sodiums, In other words, the fraction of holes filled is 1. We fill all the holes, and we've got a closest packing structure there, then we will get a 1-to-1 stoichiometry. If we fill every second octahedral hole, so for example, I think it's probably better to show in this thing, we've got a quarter of an octahedral hole at this edge. If I start to build up the next cell, just to imagine the next cell along in the cell, that's going to make, you can now see that I've got a half of an octahedral hole. And if I stick another cell on top here, I'll be getting another half. And I need to put 4 cells together that share that edge, and I will make the octahedral hole. So what I have on each edge of the cube is I've got a quarter of an octahedral hole. And I've got an entire octahedral hole, a whole hole, if you like, a whole interstices, like these are, in the middle here, which is empty. And I've got, that counts 1 because it's all inside the cell, it's not shared with any other cell. And on each edge I've got a quarter of an octahedral hole. And how many edges are on a cube? 4 on the top, 4 on the bottom, and 4 up the side. So there are 12 edges, 12 quarters is 3. So I've got the big one, the entire hole, the entire interstices plus 12 quarter holes makes 4 tetrahedral holes, sorry, 4 octahedral holes in a cubically closed packed cell. There are 4 atoms in the cell. I think we did this in one workshop a couple of weeks ago. There are 4 atoms. It might look like there are 13 or 14, but there are 4 because that is half an atom because it is shared between 2 cells, half there and half in the next one. Those are 1/8 of an atom because they are shared between 8 cells. I've got that one here, one here, one here, and then one here, one here, one here, one here, all of which share that corner. So that counts as an 1/8, and there are 8 corners in a cube, so that's 1, and there are 6 halves. 6 halves is 3, 3 and 1 is 4 again. So there are 4 atoms in a cubically closed packed shell, and there are 4 octahedral holes. Fill all the holes, you get a 1-to-1 compound, so you get sodium chloride. Fill half the holes, let's say I fill that one, but I leave that one and that one vacant. And then if I fill that one and then that one and that one, I'll still be able to make a 3-dimensional structure, but I will have a lower coordination number. That is the structure of cubic titanium dioxide, because now I've got a 1-to-2 stoichiometry. So if I fill half the holes, I'm going to have a 1-to-2 stoichiometry like titanium dioxide. That makes sense because oxygen is 2-, and titanium is in group 4, it's 4+. So it makes sense if you fill half the octahedral holes. And all you need to do to predict a sensible structure is just know inside-out CCP geometry that it's got 4 lattice point positions, 4 octahedral holes, and 8 tetrahedral holes, because each corner is a tetrahedral hole. Take the corner off, put the corner back on again, I've made a tetrahedral hole. And a cube has got 1, 2, 3, 4, 5, 6, 7, 8 tetrahedral holes. There's the 1 octahedral hole in the middle. And so that it's got twice the number of tetrahedral holes as it's got lattice points to start with. So therefore, if we fill all the tetrahedral holes, we'll get a 1-to-2 compound. So it's twice the number of tetrahedral holes as there are atoms in the first place. And if we fill half the tetrahedral holes, we'll get another way of having 1-to-1, but a way that has 4 coordination rather than 6. So there's another way that we fill half the octahedral holes, and that is if we fill all of them in one layer and then we leave a gap in a layer, if we put it that way around. If I fill the octahedral holes here, leave these ones empty, and then fill those, I will get a layer structure, and that is known as the cadmium chloride structure. It's another one of the classic structures, and that gives you layered compounds, which tend to be very friable, not very stable structures. So if you fill the tetrahedral holes, because there's twice as many tetrahedral holes as there are lattice points, You fill all of them, you get a 1-2 stoichiometry, you get fluoride. Calcium fluoride, get CCP. If you fill half of them, you get the cubic form of zinc sulfide, which is known as sphalerite or zinc blende. And again, that's a 1-to-1 stoichiometry because it's half the tetrahedral hole. There are twice as many, it's 8 tetrahedral holes, 4 octahedral holes. Right, so we've done that on the model here. Let's do it on what you've got in your handout. There is a picture of some cubic lattice. There's layer 1, there's layer 2. There is an octahedral interstitial site, also known as a hole. 1, 2, 3. There's a tetrahedral hole hiding underneath. Let's just go back. If we look there, I've got highlighted 1, 1, 1, and then this one stuck on top there generated a tetrahedral hole. And I've got another tetrahedral hole if I stick another one on top of these 3, but easier to see that one, but there will be a tetrahedral hole in there. So put that one there, that's one tetrahedral interstitial site. And that's the other tetrahedral interstitial site. So there's twice as many tetrahedral sites as there are octahedral sites. But if everything else is the same, I'll just strip down this to the octahedron again. Just make that into a tetrahedron. Okay, there we go. Tetrahedral hole, octahedral hole. You can see that is bigger than that. Yes? Simple, but that's an important result, because if I've got a big ion, it will go in there, and if I've got a little ion, it will go in there. Simple as that. Bear in mind also there's twice as many of them as there are of them. Right. So when CCP and HCP holes are filled with the atoms of their ions, and looking at CCP, here's another nicer picture, I guess, of sodium chloride lattice. So there's our face-centered cubic lattice shown as pink spheres, and our metals are shown as blue spheres here. The central octahedral hole is emphasized by the grey layer, so it just shows the faces of the octahedron, and there's the blue ion sitting in the hole. But of course, these are all sitting on quarter sites. There's, well, basically those, that is this and this. That, yeah, that's that one, that's that one. So I think 3D models are better than pictures. But there is a picture, again, you can see the face-centered cubic lattice, one at the corner, one in each face. And now we've got all the tetrahedral holes filled. You can see the tetrahedron emphasized there. And that is the structure of fluoride. So that is the structure of NaCl, or most of the alkali halides. That is the structure of calcium difluoride and many other ionic 2-to-1 compounds where you've got a big ion and a little ion. So we really need to say about that. It's quite a lot already. There is another view of good old rock salt. Again, that particular view shows you the sort of layering. We've got the blue layer, and then the chloride layer, then the metal layer, and the chloride layer. Blue is sodium, chlorine is yellow. The coordination environment of the cation is quite easy to see, because the one in the middle is contacted with an atom above, an atom below, an atom on each end. I mean, it's sitting in an octahedral hole. So its coordination environment is obviously an octahedron. Slightly less obvious is the fact that the anion positions and cation positions are exactly interchangeable. I could have a perfectly acceptable unit cell. There's an alternative unit cell that I could have chopped the structure there. So it's also a face-centered cubic lattice of sodiums with chlorides in the holes. And so the connectivity of the anions is also octahedral. And we can talk about connecting those octahedra and they share edges. I'm not going to emphasise that as much as the previous lecture did. That's a reality. Don't worry too much about that. Right, counting atoms. So this is something I talked about but didn't write much down, and that's because I knew it was coming here. If they're entirely in the cell, they count as whole atoms. If they're on the face, they are shared between two cells, so they count at half. If they're on the edge, they're shared between 4 cells, so they count at a quarter. And if they're on a corner, they're shared between 8 cells, so they count 1/8. So 8 times an 8 for the chlorides, 6 times a half is equal to 4, and 12 times a quarter plus the whole 1 times 1 is equal to 4. So the unit cell formula of sodium chloride is Na4Cl4. How much of that have you got? Yeah, you've got all that there. Right, okay. So we've already spoken about that, so we can move on. The empirical formula, it's a one-to-one compound, NaCl, of course. Right, so just to emphasise that again, I think you've got all of this as well. Cubic close packed has got 4 atoms in the cell, it's got 4 octahedral holes, it's got 8 tetrahedral holes. So the number of atoms, 8 times an 8, 6 times a half is 4. The number of octahedral holes is 1 plus 12 quarters is also 4. And the number of tetrahedral holes, there's 8 of them, because there's 1 at each corner. If you know those facts, everything else flows from those facts. So if you've got the close packed anion lattice with all the octahedral holes filled, you get 1-to-1, rock salt. It's a 4-to-4 stoichiometry, in other words, 1-to-1. If you have the anion lattice with all the tetrahedral holes filled, so if it's a cubic close packed anion lattice with all the tetrahedral holes filled, then that means you've got twice as many metals as you have anions. So that applies when you get something like sodium 2 oxide, O2 minus sodium 1 plus, and that is known as antifluoride because it's like fluoride, 2-to-1, but it's the other way around. So with fluoride, it's actually calcium is at the corners. So these that is the fluoride cell face-centered cubic calcium with fluorides in the middle. It is also, hey presto, the antifluoride cell. Now those are oxides and those are sodiums. The structure depends on the stoichiometry, it depends on the fundamental geometry. That's all, really, in that case, because they're very ionic. Ionic bonding doesn't care about direction, it's just how do you pack things together. Right, so if you have the close packed anion lattice with half the tetrahedral holes filled, then that's also 1-to-1. And that's what you get with zinc sulfide, because if you've got a sulfide anion lattice, then the zinc's going to rattle around in the big tetrahedral hole. It'll be happier, nice and snug in the little. So if it's going to be unhappy in the octahedral hole, it'll be happy in the tetrahedral hole. So because zinc relative to sulfur is rather small, it goes into half the tetrahedral holes rather than being like sodium chloride. So just the fact that it adopts that structure tells you that the bonding is between two ions of different size. It also tends to indicate that the bonding is more covalent, because if something is ionic, then how do you get hybrid orbitals that make 6 bonds or 8 bonds? It's not very easy. But if something is 4 coordinate in a tetrahedral hole, that's easy, sp3. So filling tetrahedral holes is actually not restricted to ionic compounds. It can cope with quite a lot of covalency in the bonding, which is the case of zinc sulfide, because zinc's there and sulfur's there, they're not far apart. Right, so the reason that not everything just behaves itself and forms a sodium chloride lattice, which is the simplest sort of one-to-one structure you can get. Why is everything one-to-one not sodium chloride? It's because different ions pack different ways, and also because some things are less ionic than others. So if you've got, we'll probably return to this in lecture 2 actually in a little bit more detail, but for now, if you've got a cation which is just a bit smaller than the anion, if the radius ratio of cation to anion is just somewhere between 1 and 0.7, then you'll get sodium chloride. If it's closer to 1, if they're the same size, then you'll get cesium chloride, which is light body centered cubic. But if the radius ratio is much less than 0.7, then you'll get zinc blende structure, the zinc sulfide structure, which is like this, but with half the tetrahedral holes filled. So zinc 2+ is too small to contact all the anions if it's in an octahedral hole, so it goes into half the tetrahedral holes, which you get coordination number of 4 in each ion, and that's also better able to support some covalent contribution. So not everything that's a lattice is necessarily highly ionic. You can in fact describe the structure of diamond as exactly analogous to the structure of zinc sulfide. It's a cubic close packed array of carbon atoms with carbon atoms in half the tetrahedral holes. Completely covalent bonding, perfect covalent bonding, they're all the same atom. And it's obviously a very robust lattice. So that's the structure of diamond. Okay. And we're started a little bit late, if you indulge me to overrun for a bit. We'll certainly not get as far as Miller indices. We'll try and finish the whole coming bit. There is another picture of fluorite, again showing red atoms on the corners and the faces. That's the face center cubic array of calciums with fluorides in all the octahedral holes, which gives you the 2-to-1 stoichiometry, because all the tetrahedral holes are entirely within the cell. They all count a whole number, so there are 8 of them. And that's there in comparison with the zinc blende structure, because that's the same face center cubic lattice, but this time the lattices are sulfides and the zincs are in half the tetrahedral holes. That one and that one, not that one and that one. Just the same, but that one maps to there, that one maps to there, that one and that one are vacant in this one. So that's a 1-to-1 stoichiometry as well. That's exactly the same. If they would made them all the same structure, all the same colour, they're both float coordinate, sp3 all the way. That's the structure of diamond as well. Right, so the cation coordination in calcium difluoride, fluorite, is cubic, because you can see that you've got 4 going down there, 4 going down there. The next cell stuck on top will have 4 there and 4 there. It's going to be cubic. And the anion combination is tetrahedral. Don't worry about the connectivity. Antifluoride's the other way round. In zinc blende, both the cation and the anion are a 4 coordinate. Easy way to remember that is also diamond. It's bound to be 4 each, because you know that carbon make 4 bonds. Okay, so in hexagonal, just for completion, you also get structures that are exactly analogous, but instead of packing a cubic close packed lattice, you're filling octahedral and tetrahedral holes in a hexagonal lattice. And the difference between hexagonal and cubic is that you've got octahedral holes, and you have again one octahedral hole for each lattice site, and so you can get 1-to-1 stoichiometry. That's the thing which is common to rock salt. The difference is that if you fill all the octahedral holes, then what you get left with is the anions are in a trigonoprismatic geometry. So the thing to remember is that if it's hexagonal, generally it's not very ionic, because you end up with this trigonoprismatic geometry where you've got a triangle, another triangle straight on top of it. That doesn't really work with electrostatic repulsion, that indicates covalency. So if something's hexagonal, it's more likely to be covalent. And there's arsenic there, there's nickel there, they're not far apart. So that makes sense. What you don't get is there is no hexagonal version of fluoride. It's impossible to fill all of the tetrahedral holes in the hexagonal lattice. If you did, you'd have one there or one there, and they're too close. So there is no structure with both tetrahedral holes full. Now if you fill half the tetrahedral holes, you get hexagonal zinc sulfide. Zinc sulfide has got both a cubic and a hexagonal form. The hexagonal form is known as wurtzite. Okay, so that's for information. We'll do more about that next time. That's another summary. And we'll need to consider the rest on Monday.